On Tesla AI Day, Andrej Karpathy, the director of AI and autopilot vision at Tesla, enlightened us with a presentation about their self-driving neural network. To save you time, I have outlined the general concepts so you get a sense of how intelligent Teslas truly are. At the start of autonomous driving development, the main objective was to let the car move forward within a single lane and keep a fixed distance from the car in front. At that time, all of the processing was done on an individual image level. The feature extraction flow or neural network backbone. The raw images of the car camera are processed by a residual neural network, RegNet, that extracts multiple blocks or feature layers in width, W, X height, H, X channel, C. The first feature output has a high resolution, 160 by 120, and focuses on all the details in the image. Moving all the way to the top layer, with a low resolution, 20 by 15, but with a greater channel count, 512. Intuitively, you could visualize each channel as a different filter that activates certain parts of the feature map or image. For example, one channel puts more emphasis on edges and another on smoothing parts out. Therefore, the top layer puts more focus on the context by using a variety of channels. Whereas, the lower layer focuses more on the details and specifics by using a higher resolution. The multiple feature layers interact with each other via a BiFPN, a weighted bidirectional feature pyramid. For example, the first detailed layer thinks it sees a car but is not sure. At the top of the feature pyramid, the context layer provides feedback that the object is at the end of the road. So yes, it is probably a car, but it is blurred out due to the distance. The output features are not only used to predict cars but are used for multiple tasks such as traffic light detection, lane prediction, etc. Each specific task has its own decoder trunk or detection head, which is trained separately, but they all share the same neural network backbone or feature extraction mechanism. This architectural layout is called a HydraNet. So, why this HydraNet? Feature sharing. It is more computationally efficient to run a single neural network backbone. Decouple tasks. You can fine-tune tasks individually without affecting other predictions. This creates more robustness. Now that we understand how the network works for individual images, we can ask ourselves, how do we combine multiple images into a 3D space? After all, we want to have a thorough understanding of the surroundings, especially if the car is self-driving. Tesla's engineer developed an occupancy tracker in order to stitch all the camera images together. How do you transform features from image space to vector space? Instead of stitching the images explicitly by hand, you want them to be part of your neural network, which will be trained end-to-end. The image space predictions should be mapped on a raster with a top-down view. The first challenge is that the road surface could be sloping up or down and there could be occlusions due to cars passing by. So how do you learn a model to overcome visual barriers? If there is a car occluding a viewpoint, you want to learn to pay attention to different parts of the image. To accomplish this, a transformer with multi-headed self-attention is used. Essentially how it works is that a raster is initialized with the size of the real-world output space, vector space. The yellow pixel, at a known position in that output space, will ask the neural network with the 8 cameras for information about that pixel, the query. The keys and the queries interact multiplicatively and then the values get pulled accordingly. After some processing, the output will be a set of multicam features about that pixel that can be used for predictions. To make this work, precise calibration and good engineering are key. If you build a car, the cameras will always be positioned in a slightly different way. Before you feed images into the neural network, you need to calibrate the final result is a big performance improvement and better predictions coming directly out of the neural network. After we have the image prediction right, we still need to consider another dimension, time. Adding time to the equation. There are a large number of predictions that need time or video context. For example, if you want to identify whether a car is parked or traveling. If it is traveling, how fast is it going? If you want to predict the road geometry ahead, the road markings 50 meters ago can be helpful, etc. Multi-scale features are generated by the transformer module and are concatenated with kinematics, such as velocity and acceleration, as well as the tracking of the position of the car. These encodings are stored in a featured queue which is then consumed by a video module. Time-based queue. The latest features are pushed to the queue within a specified time frame of milliseconds. If a car gets temporarily obstructed, the neural network can look at the memory and reference it in time. Therefore, it can learn that something is occluded at a certain point in time. Space-based queue. In order to make predictions about the road geometry ahead, it is necessary to read the line marks and road signs. Sometimes they occur a long time ago, and if you only have a time-based queue, you may forget the features while you're waiting behind a red light. In addition to a time-based queue, there is a space-based queue, and information is pushed every time the car travels a certain fixed distance. The feature queue is consumed by a spatial recurrent neural network, RNN. The RNN keeps track of what's happening at any point in time and has the power to selectively read and